Alina, you're still muted. We cannot hear you. We see your slides though.
Yeah, hi everyone. Can you hear me now?
Perfect. Thank you.
Yeah, great, thank you. So, my name is Alina Shadrina, and I am technical consulting engineer at Intel. I'm working mostly with compilers. And so today we are going to talk about Fortran and OpenMP offloading in Fortran. So yeah, today's agenda is quite, short, but well, we will learn how to offload code to the device using OpenMP, how to synchronize memory, and we'll see some tricks that helps you to work with runtime, to debug runtime issues, to see which information you can get from the runtime. And today's presentation is focused on Fortran, but I have prepared short hints both for each statement, for C++ and for Fortran, if it is important, if there are some differences. And so we are starting from the compiler. Yeah, OpenMP float constructs were introduced in OpenMP 4.0. In general, the offloading is needed when we are talking about heterogeneous systems. We have host, which is usually a CPU, and we have a device, also known as accelerator, containing some execution units. And the device is usually a GPU, or and the execution model is host-centric, so it means that the host offloads target regions to target. So we need a special construct to let the compiler know which code is for device and which should be executed on host. And in general, we have actually two compilers here. One is for host and the second one is for device. And as you know, host and device memory is independent. So we also need to move data between host and device. So we need a separate constructs for each of this purpose, and so we will learn one by one each of them. Let's see in detail how OpenMP offloading support is implemented in Intel compilers. Please note that you need next-gen compilers. It's ICX, ICPX for C++ drivers, and IFX driver for Fortran. Our classic compilers, ICC and iFort, do not support offloading, and there are no plans to do so. Well, what else? Let's look at the compiler line. First of all, for any OpenMP task, you need a QOpenMP option to enable OpenMP support. And after that, you need FOpenMP targets with the keyword SPIR64 to enable offloading. Actually, SPIR64 is the only supported value for this option right now. It is a 64-bit standard portable intermediate representation. This is it means that compiler generates x86 and this SPIR64 fate binary for GPU devices. I must emphasize here that you cannot use FOpenMP targets without QOpenMP or its equivalents. Here, right on the slide, you see all these equivalents. Shortly, there are three OpenMP options. It's QOpenMP, FIOpenMP, and FOpenMP. Personally, I would recommend you to forget about FOpenMP because this is a native C-Lang option. And the other two options, QOpenMP is just for compatibility with iFort for those who used iFort for a long time. And FIOpenMP is means that this is Intel OpenMP is just to mm, to make a difference between FOpenMP and FI OpenMP. So all these options are equivalent, and you cannot use FOpenMP targets without one of these options. Um, actually, it doesn't matter whether you use only offloading pragmas or your CPU OpenMP pragmas, because without OpenMP, the compiler will not recognize any OpenMP pragma. So your application will be running. So your application will be running on a single thread, and obviously it will not do any offloading. So okay, summing up, you need to use next-gen compiler, add OpenMP and FOpenMP targets option, add use OpenMP to your source code, and also I put the link here, so I would recommend you to check to make sure that you have supported GPU and OpenMP pragmas you are going to use are supported by the compiler. And also, I need to notice here that IFX is really actively developing, and it recently moved from beta to product, so please track our release notes for any updates, because there are many updates from release to release. Yeah, and also one more point here is that ahead of time compilation is supported as well. To use it, you need XOpenMP target backend option. Actually, there are three types of options created using one template. It's like XOpenMP target, and you add one keyword that you are going to, to send your options. You can work with front-end options, with back-end options, and with linker options. For ahead of time compilation, we need XOpenMP target backend, and we pass a device option. In this specific syntax, it means that you are going to target all available devices. I mean, all available GPU devices. If you are going to target a specific device, then you need to pass a short name for it. For example, Gen 9. And this is really helpful if you are going to debug your application, because ahead of time compilation moves any runtime issues to a compile time. Yeah, in addition to compiler options, there is a list of variables that give you some control in runtime. First of all, to enable offload, you can use OpenMP target offload variable with value mandatory. If you are going to debug your application, you can try this variable with disabled to make sure whether the issue is reproducible on CPU or not. And please note that in fact, the behavior with disabled value is implementation defined. So other compilers may behave in different way if you use other runtimes, sorry, may behave in different way if you pass this option. Always, I always recommend you checking docs. And also, you can control runtime backend with libopenmp target plugin. There are two values here. It's OpenCL and level 0. By plugin, we mean an intermediate layer, software layer. It's in short words, it's higher than hardware drivers, and it's lower than compiler runtime. it's needed to implement some abstractions that are too high level for drivers and too and too that right too high level for drivers. So sometimes we refer level 0 and OpenCL as backends or even drivers. So in these topics, all these words are equivalent. So if and why this variable can be useful? If you see some runtime crashes or unexpected results, try to change your backend first and see what happens. Also, there are 3 more options for debugging. The first one is obvious. It's libopenmp target debug. You can use any level of details. Start with 1 and try to and see whether you have enough information on this level, or you need more information. If so, then just try to use 2 or 3 or more. I'll show you in the demo part how the debug log changes depending on the value you are giving to libopenmp target. By default, it is 0, so it indicates that no offloading runtime debugging information will be printed to the standard output. And yeah, I must tell that just be careful with this option because it generates really huge output. So it may be, it's better to redirect it to the file. And oh, well, okay. The next option is libopenmp target profile. It is a performance profiling variable. So it gives you, it will track GPU kernel start complete time and some data transfer time that will show you what really happened with your kernel. And the last variable is libopenmp target info. It gives you information about kernels and data mappings. I will also show you a bit more on the demo part. And also, I would recommend you to refer level 0 specification because this backend was created for one API, and you may be interested to learn more about it. So yeah, this is a general overview of offloading constructs. We will discuss all of them today, and as you see, there are three groups of constructs. Constructs that help us to tell the compiler which code is for a device, some work sharing constructs, and constructs that are responsible for memory operations. Yeah, this is to show you the difference in syntax. Pay attention to the fact that some pragmas require AND in Fortran and it's never used in C++. And yeah, now let's consider the first block of that OpenMP constructs. This is a very simple example. I will incrementally change it during this presentation, and I do not recommend you running the code from this slide as is. I'll give you a short compilable example at the end, but on these slides, it is just code snippets. It's not intended for to be compilable and runnable. So as you see, it all starts with host code. In this blue box in top, we have 3 arrays, A, B, and C. We are assigning some values to A and B. And after that, you see the green block, starting with OpenMP target pragma. So this pragma transfers the control flow to target device. So target directive offloads the code after this pragma until the end target pragma of the device. And actually, what happens under the hood is that this pragma creates a task on a device. And OpenMP task is an independent unit of work for that will be executed on threads, including your code, data, internal control variables. So this is a task, and host in this point, host thread is waiting for a device now because by default, target region is sequential and synchronous. You can control it just adding no wait function, no wait after target to let the host perform the next line of code after the region. It's like, so it will in parallel starts offloading the code to device and move to this print loop. In this specific example, if I add no wait, write will just not make any sense. We will print empty array, or we will print any trash, or anything that is not actually, it's not actually what we are expecting here. It's not the result of vector addition. And well, in this also you can organize the execution order if you have several target regions. You can use keyword depend to synchronize tasks between each others. So in this exactly example, we do not have such we do not have depend or no wait, so the host is waiting for when a device is working on vector addition, and after that the device returns the control flow to host, and we can print the results. So this is how to specify the device for offloading in case we have multiple accelerators on our system. You can just pass target device keyword and number of your device. Actually, the device number is an integer. It usually starts with 0, and it is actually implementation defined how your multiple GPU devices are, how numbers are assigned to your GPU devices in your system. Yeah, a couple of slides ago, I told that the code inside target is synchronous and sequential, but we are talking about GPU offload, right? And so in this case, what is the benefit from using GPU if it is sequential? GPUs are massive parallel in their nature, so we need to make our loop parallel. For those who are familiar with OpenMP, there is maybe an obvious solution. Let's just add OpenMP parallel do here. But in fact, this is not a good solution. And this is actually not an optimal solution. The reason is that architecture of GPU and CPU are really different. And OpenMP initially was created for shared memory systems. So all threads are sharing the same memory. We have only, one level of parallelism. However, GPU actually contain multiple subslices. And this construct, if we will write just as is, OpenMP parallel do, this construct will be executed only one subslice only. This is because there is no synchronization among subslices, and there is no coherence and memory fence among subslices caches. So I will show you the next picture, and you will see how many performance we are losing in this case. You see, this is a Gen 9 architecture, and you see that there are 3 slices. Each slice contains 3 subslices. So you see that if we will execute our loop on one subslice, we will lose at least 8 subslices. So they will be not perform any useful tasks. And in fact, Teams construct gives us a desired level of parallelism. Teams creates multiple master threads inside target region, and each master thread creates a league of threads. Threads are synchronized only inside one team, and because there is no synchronization across teams of threads, the team could then be assigned to different GPU subslices. There is no synchronization, as I said, between teams, so barriers, critical sections, atomics, and so on are legal only within the team. Otherwise, you will just lose this independence between subslices, and so it really leads to losing massive parallelism. And so, one question here, actually, how to determine how many teams we can create on our device? And I would recommend you using CASTIEL info tool, which is delivered in one API, so you can or you can install it. So when you run CASTIEL info, find your GPU and check number of work groups. And this is the answer: how many teams you can use for your GPU. Yeah, this is a picture illustrating almost everything that I told earlier. So you see some slices, you see 2 thread teams, and how OpenMP constructs are mapped to GPU hardware. You see that OpenMP team is mapped to group of threads, and it is working on the subslice level. OpenMP threads are working on execution unit level, and that's why actually we can't just use parallel do in target constructs. So we are talking about teams, and now we can make this construct even more complicated. And distribute keyword will give us an opportunity to distribute iterations of a loop across the different teams. This construct actually can be nested in target region and perform any work sharing within the team. On the slide, you can see a more correct way how to implement parallel do on a device. Actually, you need target teams distribute parallel do. And this picture illustrates you what actually happens if you are using distribute parallel do. Imagine we have 100 iterations. And in this case, if we have 2 teams, then we will distribute 100 iterations into 2 teams by 50, iterations for each team. And each thread will execute 10 iterations. So yeah, one more useful thing here it's clear that sometimes we need to call a function within the target region. It's not enough just to call it. We need to recompile your code first for a device. And remember, device code is always compiled by a separate device compiler before running. Declare target construct ensures that procedures and global variables can be executed or accessed on a device. So if host specifies only a host version, so if you use host, you will use only host version. No host will compile you a host and a device version. Sorry, no host will compile you only a device version, and any device type will compile you both host and device. So yeah, in this short summary, you see that we have learned in the previous blocks all the work sharing and device code constructs. And the next one is work sharing. Oh, sorry, the next one is mapping. Yeah, so actually target constructs do not move your data to the device. You need actually target map. So we have end target that creates scope for a float region, and this is only about code that is to be executed on a device. Now we need to move data to a device to perform vector addition. We need map construct here and assign map type for each array. For example, A and B contain data. We are going to read them and they are not expected to be changed. So we will use to with them, and it means that we are going to copy data to the device on entry to a target region. But we are going to store the result in C array, so we are going to use to from. And firstly, we created it on host, and it is empty. So we are moving it to a device by using this construct. There are other modifiers like alloc, release, delete, and so on. And I hope that the difference is quite, clear. You can allocate array on a device, and you can release the memory. For dynamically allocated data, the syntax a bit differ. You see that there are differences between C++ and Fortran, and pay attention to the fact that in C++, for dynamically allocated arrays, you are passing start and length of the memory that you are going to move to the device. And for Fortran, you are passing start and end indices of the array. Also, there is a solution how to minimize data overhead. Because, well, what if we have an array that is used in many offloading regions and it never changes? In this example, we are reading A and B in 2 regions. And actually, when we leave a flooding region, data environment is destroyed. So we have to copy A and B twice. And it's really overheaded and gives negative impact on performance. And to avoid, you could use target enter data and target update constructs. And on the next slide, like you see, this is how it actually looks like. We have 2 target regions. We need to synchronize data with host using target update. And now we can continue using it in the other region. And well, so this is all with OpenMP constructs. And a short demo looks like, looks like we don't have much time, but demo actually is actually short. So we have matrix multiplication sample here, and okay, so we have matrix multiplication sample here, and we are going to compile it. with Intel Fortran compiler, and yeah. So I would remind you to run source for before running compiler, and I'm using module files here. So, well, we are compiling the code using OpenMP and OpenMP targets options. And actually, I'm exporting this variable to offload my region on GPU and running the sample. So you see that it's just not many output here. But if I'm using libopenmp target debug, you see how many output we have. It describes in detail what happens with your memory, how your kernel was compiled, what happened with memory objects, and so on. In a very there are very detailed logs, so you can play with values here and see as much details as possible. Also, you see a backend which is used in your runtime, and you can even switch your backend to OpenCL using this variable and run again and see the difference in logs. And actually, I've prepared this different using diff tool, so this log is generated with one libopenmp target debug value, and this one with 3. So you see that there are so many details in with the level 3, right? And I would recommend you playing with all these variables for the better results. And this is, I think that's all for today, because I see that we are running out of time. Thanks for your attention, and let me check whether there are any questions.